So you have a problem. Given a set of words, let's say cat, dog, monkey, you're supposed to check whether a given word is present in that set or not. Say the given word is short. Pause the video and think of a simple solution to this while I see what's the problem with this shitty cat. Okay, so a simple solution to the problem would be to iterate over each word in the set and compare it to the given word. But this solution is shit. Why? We can do better. The time complexity of this solution is big O, the length of the word given, multiplied by the number of words given in the dictionary or the set. We need a solution in big O of the length of the word given. I'll say it like big O of x instead. So again, pause the video and try to think of such solution. Another solution to this problem is hash tables. We can put all the words into a hash table and then try to retrieve the given word. But it's not that simple, as we need to find a good big O of length of the word, or big O of x, say it, a hashing function, and we need to handle collisions well. So we can still get a better solution than this. Here we can use a trie. The best way to explain a trie is through an example. As you can see, a trie is a tree where each node links to the remaining part of given strings. For example, let's search for the word cat. Through the first node we can find C. Then A is a child of C, hence we can find A, and T is a child of A, so we can reach D. D is marked as the end of word node, it's a leaf node here. So we found cat in the trie. Let's search for the word shark as another example. We can see there is no link to the letter S, hence shark is not found in the set. Time complexity of this method is big O of x, the length of the given string. So how do we construct a trie? First, here's how a trie node looks like. For simplicity, we'll suppose the alphabets consist of 26 lowercase letters from A to Z. Each node will carry 26 children that possibly link to other nodes. When we don't have a link, we set them to null. EOW means the end of a word, is to tell that we reach the end of word in a trie. The implementation here has nothing so fancy, and I will provide the code link in the description. One important thing to add is a function that creates and initializes a node. First, we allocate a new node in heap. Next, we initialize all children to null. We initialize EOW to 0, not null, apologies for that. Finally, we return the new node. Now we want to insert a word into the trie. We need to loop over the word and the trie at the same time. Each time we advance to the next character in our word, we check if that character is a child of the current node. If the child exists, then we advance to that node. If it is null, we create a new node and place it there. Then we advance to that node. We do that until we finish looping over the word. Finally, we set the last node's EOW to 1. That will mark our end of word in the trie. The code is very simple. Make a current node starting from the root. Loop over both the key and the trie. Check if a child node exists at the current node and the index of the current character. If not exists, create it. Then advance to that node. After the loop ends, set EOW to 1. This indicates that the last node inserted is the end of the word. Searching for a word in a trie is very similar to inserting one. Pause the video and try to think of a way to check if a given word is present in a trie. Write code and test it. Okay, so to check for a word in a trie, we loop over both the word and the trie. Then we check if the child at index of current character of the current node exists. If it doesn't, then the word doesn't exist and simply return 0. Otherwise, we keep looping till the end of the word, and we check if the final node has the EOW flag set to 1. If it does, then return 1, 0 otherwise. The code is very similar to the insert function. We start with defining the current node, then start the loop. If a child node we need doesn't exist, then the word doesn't exist, and we return 0. At the end, we check for EOW if set to 1. Return 1 if set, 0 if not set. To check if a trie is empty or not is simple. Pause and try to find a solution and write code. A trie is empty if the root is null, or if it has no children. The code is a straightforward implementation of this. Deleting a word in a trie is not very easy. When deleting, make sure not to delete nodes that belong to other words. We will write a recursive function for deleting. It goes as follows. Iterate over both the trie and the word. If a node is empty, then delete it. Let's look at an example. Remember, the function is recursive and deleting will happen after the recursive call. First, C exists, so we advance. A exists, same thing. T exists, we advance to the last node. The word reached \0, which means we're done iterating. Now we check if the current node EOW is set. If it is set, we unset it. Then we check if it's an empty node. Here it is empty, so we delete and set it to null. This is a base case in our recursive call. Remember, only delete if a node is empty. Now going back, the A node is now empty, and it is not an EOW, so we delete. Same for C, thus we deleted a word from the trie. If EOW is set, we couldn't delete.
Here's the code for deleting. I suggest you pause at times and read carefully to fully understand what's happening. Note, I am incrementing the key in every call, so the key represents the current character. Here's a final test using all the functions we wrote. As you can see, shark and dogs aren't present. Cat was present before deletion. After deletion, it was not present anymore. There is more to tries than this. As a homework, I want you to modify the trie to get the number of words that start with certain prefix.